Welcome to my TED Talk, a talk on central processing units. Here's my research question. To what extent do specific factors such as clock speeds, parallel processing, cache size, influence the performance of CPUs and how these interactions affect hardware components in a computer system? Now, what are central processing units? Well, this is a central processing unit, and it's basically the brain of a computer. Their job is to basically carry out tasks, background tasks, and applications. Whenever you go through your computer and let's say you click on Google Chrome, the CPU is doing that job for you. Now, how does this all work? Well, it starts with the control unit of the processing unit, and basically what happens here is the control unit is responsible for basically operating, like taking care of all the operations that the CPU goes through, and it makes sure that everything runs smoothly within the pipeline process, which we'll get to in a second. And it makes sure that everything and all the data is processed correctly. Now here is the pipeline process. On the left, you see the pipeline there. This basically has 4 stages, and the first stage being a fetching stage. What happens here in this stage is basically the CPU will communicate with the RAM or main memory and other memory types which are listed here. And it will find the memory type within any of these memory categories, and it will pull operands or data from that section that it's looking for, and it will start its operations. Basically, the way this works is that once the data gets to the CPU, the instruction basically tells the CPU every time in the process what it has to do next. So this is where the memory management control unit comes in, or memory management unit. And this basically operates by fetching, by quickly translating a virtual memory address into a physical address. Basically what that means is, in the memory hierarchy that you saw in the previous slide, the CPU will translate its virtual address that it has, address being like literally where the data is stored, and then it will put that into physical so the CPU can understand it, and then that will come in later in the writing stage of the CPU. And this memory management unit also helps keep data moving smoothly throughout the process, and helps the CPU work efficiently. And during the instruction decoding stage, we have the instruction decoder. And the basic way that this one works is that it basically looks at each instruction and it has to determine what kind of instruction it is. Once it determines the kind of this instruction that the CPU is going to run, it will then execute that instruction. And it also looks for other things like hazards within the pipeline, like let's say if something went wrong early on, in the early stages of the pipeline, that's when the instruction decoder will catch that and fix it. So it's basically kind of like a 2-step verification, if you think about it. And so now we have speed, and speed in CPUs is measured in frequencies. So to understand this, CPUs, older CPU models were measured in megahertz, and since they're more modern now, they are measured in gigahertz. So to understand this, 1 megahertz is equal to 1 million cycles a second, which is, cycles just refers to how many instructions that the CPU does a second. So modern CPUs nowadays can do 1 gigahertz, which is 1 billion cycles per second, which is pretty fast. And now we have cores. So what you're looking at here is a microscopic image of a CPU core base. And basically what this is CPUs have these cores, and these cores, their basic job is similar to a CPU in that they do their own processes as well. So they'll go through the pipeline themselves individually and complete the pipeline. And so that's how that works. And so Then we have another method that gets applied to them. I shall mention that CPU cores are also applied in what's called parallel processing, which means that a CPU has multiple cores to work with, allowing it to run faster. So this is called simultaneous multithreading, and it is a method that can be applied to parallel processing CPUs, and basically works by shortening the time that it takes for instructions to be completed. So as you see up here, we can call this the serial computing, which basically means that each instruction is finished one by one at a time, which is very slow, but it can be used. And then next we have both of those tasks, but with hyperthreading on it. So hyperthreading is another name for simultaneous multithreading. That's just Intel's name for it. And then at the bottom there, you have both tasks with the hyperthreading, basically combining those two and this to create this. And that saves a lot of time for instruction execution. Here's a visual example of what I mean by cores and threads. So now we have threads, and threads, these are what are known as virtual threads. So basically how these work is you have your cores, and for each core you have a set of threads, and those threads help out the core to do its job faster by basically speeding up the process, doing its own mini microprocesses along the way. And so here we have a quad-core CPU. Each core has its individual threads, and those threads work to help the core do its job. And that's how simultaneous multithreading works for multi-core CPUs, which they only work for multi-core CPUs since that's the more modern technology we have now. Here's an example of in parallel processing and how this works. So on the right you see serial computing, which, like mentioned before, it does each instruction one by one and completes them in that way. Whereas parallel processing, it uses each of its cores to basically take on a set of tasks on its own. So these set of instructions can also be known as threads. It might be a little confusing, but the distinction between virtual threads and threads is basically threads are a string of instructions that run through the pipeline. Virtual threads are what help the cores do its job. And so with parallel computing, a string of threads would go through each of the cores, and this is basically the outcome of that. And here's the distinction between the two. On the left you have a quad-core CPU, four cores, its own threads, and parallel processing and serial computing, which I just explained. And then that's another reminder of how it works together. And so now where does this leave us with computing today? So with computing today, with these capabilities, we're able to take on computing to another level by allowing our computers to go faster for tasks like CPU rendering, and a good example being video games. Since CPUs nowadays, most of them can be made for video games. However, most commercial like CPUs that are used in like laptops or desktops are mainly used as like just everyday use. So having a fast processor, such as like a gaming CPU, would make a computer much faster, which means you would be able to do more with it. And so with that, the importance of this is that, well, speed. If we have faster processors, we have faster computers, which means we can do more at once. And so, yeah. Questions? Sure.
Can we just start a question for that?
Yep.
So